The world is full of problems that need solutions. The people wanted a solution to their problems, so they hired a bunch of smart programmers to look at the problems. The programmers examined the data available and examined the problems, and using maths and logic, the programmers wrote some software to process the data and output an answer. But the people weren't satisfied. They had more problems they wanted solved, and the complexity of the problems kept increasing, and the time and money spent writing programs kept increasing. And sometimes the programmers even claimed they didn't know how to solve the problems. Wouldn't it be nice if we could get solutions without programmers? All we need is for the programmers to write a program that can program itself. The program could take in the data, program itself, and generate a solution. And if the solution isn't good enough, we can just run it again until it is. Then we wouldn't need programmers anymore. Thus, the dream of machine learning was born. The modern world is full of problems looking for solutions. Better health systems, self-driving cars, voice recognition, digital assistants, the generation of cat photos. The traditional methods of software development to solve these problems haven't been able to keep up with the demands. At the same time, the amount of computational power and availability of data has exploded. Machine learning is a broad category of software algorithms which have been around in their basic form for quite a long time. However, they were computationally expensive and they needed to process a large amount of data which was beyond what was technologically available at the time. This limited their use to mostly academic research. This has all changed in the last few years with the rise of massively parallel hardware, first in the form of repurposed graphics cards, and more recently with custom hardware that has reduced the processing times down to feasible timeframes. The advent of the Internet is often considered the major advance that provided the data needed for machine learning to grow. But other means of rapid digital data collection, like digital cameras, laser scanners, digital voice recording, and smartphones, have also been essential to greatly reducing the cost to capture the data needed to drive the algorithms. This convergence of large and easily accessible data with processing power has allowed a surge in machine learning research and development, and especially in the category of neural networks. Neural networks were initially developed based on concepts of how the brain works by linking together a large number of simple neurons. Complex behaviours could result. Modern development, however, is more mathematically focused. There are many different types of neural networks based on the structures of the neurons and how they are interconnected. For this example, we will look at one of the simplest possible, one neuron that takes one input and produces one output and has two parameters, W for weight and B for bias. And we have a set of training data. We want our network, when given the inputs 1, 2, 3, and 4, to give the corresponding outputs 6, 8, 10, and 12. We could look at the data, do some thinking, and figure out what W and B need to be. But that's almost programmer levels of effort, and we're lazy. So, through the power of machine learning, let's see if the system can learn the values itself. For this, we need to introduce two more key concepts in neural networking: a loss function and a gradient function. The loss function is used to compare the output the system generates to the expected value and decide how far off we are from being correct. A very simple loss function is called least square. We take the difference between the predicted value and the expected value, and then square it, and then take the square root. For this simple example, the result is just the absolute value of the difference. So for the rest of the example, we will just use the absolute difference. There is also the concept of the cost function, which is the average of the loss function for all of the neurons. Since we only have one neuron, they are the same function. There are many different loss functions depending on the type of input provided and the output that is being generated. The smaller the loss value, the closer the system is to the required output. The gradient function is generated from the neuron function and uses the cost function to decide how to change the parameters. For this example, since the cost function is the same as the loss function, we will just use the loss function. The gradient function is normally derived from the cost function, which includes the neuron function, using calculus to generate the partial derivatives for each parameter. I think it's easier to understand how this works if we use an alternative method. In this example, we will use numerical approximation instead of mathematical derivatives. We start with W and B equal to random values, 0.5 and 0.5, and we run our data through our network and see what we get. So, our neuron is pretty crappy at predicting the answer. So we need to adjust the parameters to give us a better answer. But which way and by how much should they be adjusted? Let's use just the third value to make this a bit simpler. We input 3 and got out 2, but we wanted 10, so our loss value is 8. What if the parameters were a bit different? Let's rerun the computation with slightly different values for W and B. From the table, we see that increasing W reduces the loss, but reducing W increases the loss. Similarly, increasing B reduces the loss, but reducing B increases the loss. The change of the loss over the distance, in this case 0.1, is the slope of the function, or gradient. We can see that changing W makes a bigger difference than changing B because it has a larger slope. So let's change W and B in the direction that lowers the loss. For W, that's 3, and B, it's 1. Making large changes can lead to problems, so we will scale the change, or step size, down by dividing by 10. Managing the step size is an important part of tuning a neural network. Too large, and the system can be unstable or circle around the answer. Too small, and it will take forever to train. Great. Now we rerun it again using 0.8 and 0.6. And now we are closer to the correct value. The system keeps repeating this over and over, adjusting the values of W and B in whichever way causes the loss to decrease. In a real system, it's a bit more complex as we try to optimize the changes so that we can get to a solution faster and try and avoid overshooting the answer. But the basic principle is the same. Keep adjusting the parameters in whichever direction reduces the loss. After 9 iterations, W equals 2.9 and B equals 1.3, and our function returns an answer of 10. Yay! Which is the answer we were trying to get. Unfortunately, it doesn't do so well on the other values. For example, 4 returns 12.9. Neural networks depend on the data they are trained with. It's important that the data used to train the network is representative of the data that it will be used with. So, instead of using just 3, we train it using all the data. But first, we need to update our loss function. We simply take the average loss for all the inputs. This grid represents a range of values for W and B. Let's see what happens to them as we run our gradient process. Why does it follow that path? Here, the height represents the loss value. We can see that when beginning training, it goes down the slope to the valley in the middle, and then the valley slopes gradually away from us. Towards the end, the values start to oscillate because our step size is too large and it keeps overshooting the best answer. To fix this, While running the training, the step size was gradually reduced, so eventually it settled on an answer. It will calculate w equals 2 and b equals 4 after around 3,000 iterations. With better tuning of the step size and using other optimizations, a real neural network can be made to converge more quickly. This tuning is a major part of making a good neural network. A real neural network consists of more than one neuron in one layer. You can have 16 neurons in a layer or 32 neurons in 2 layers. Commonly, every neuron in a layer takes as input the output of every neuron in the preceding layer, which is a lot of connections even at this simple stage. Each input is given its own weighting. The neuron function thus becomes the sum of the inputs times their weights plus the bias. This leads to the number of parameters quickly climbing into the thousands for even a simple network. Neural networks to understand speech or generate images can run into the millions of neurons. The processing costs of neural networks are very asymmetrical. While the training costs skyrocket for large networks, the evaluation of the network, once trained, can be surprisingly quick. The majority of the processing time and cost is during the training phase and depends on the size of the network and the amount of data. In our example, once you have the values for W and B, you can compute the answer in your head in a second. But running the process to train the neuron took over 3,000 iterations, which would take hours to do by hand. When scaled up to thousands or millions of neurons, neural networks can perform some amazing feats that rival or exceed what humans can achieve, and perform tasks which previously were slow and error-prone to a level that allows entirely new possibilities to emerge. It's difficult to see how all this can be produced from just a collection of simple neurons without any clever mathematics or programming. This understanding of how neural networks function on a large scale is a topic of current research, but some insight can be found in the concepts of emergent behavior and complexity theory, sadly topics beyond the scope of this presentation. For now, we can simply enjoy the fact that it does work in many complex areas where no other methods have succeeded. Challenges still remain, however. It's still very computationally expensive and needs a lot of data to train the network. Also, there are a number of problems that can cause your network not to converge onto the best solution, or even onto a solution at all. And even when they work, they often generate only an approximation to the real solution and a probability of giving the wrong solution on some input data. So, an approximate answer with a chance of giving the wrong answer that takes a long time to make work. That's almost a perfect approximation of the average programmer. But if you understand your data and understand both the power and the limitations of neural networks, they make possible solutions to problems that were previously unsolvable, or make amazing improvements to existing solutions.
And so the people got their wish. And the programmers made a program that could program itself. Once the data was properly organized, and once the parameters of the program were properly adjusted. And so they stopped needing programmers to write programs. And all the programmers became data analysts because they were suddenly in big demand.